Welcome to today's Research Pays Off. I'll now hand it over to our speakers, Drs. George Chang and Cesar Tirado.
Thank you, Lauren. I have to say it again. Good morning, good afternoon, and good evening for those overseas attendees. Welcome to this Research Pays Off to present what we have just wrapped up for the NRRA research project in March. It's a long title. It's called Evaluation of Levels 3, 4 Intelligent Compaction Measurement Value for Soil Subgrade and Aggregate Subbase Compaction. Mouthful. But you can find out more information about our work plan detail from our the mndot.gov project website. We're also going to publish a paper, final report soon that will include a lot more detail. So just kind of quick brief history about intelligent compaction that was invented back in the 1970s by the geodynamics. And then in 2000, that used to be called CCC, Continuous Compaction Control. Back in 2004, that's when the Federal Highway in the US have written an IC Intelligent Compaction roadmap that coined the intelligent into the compaction, the terminology. In 2007, that's when we started a profound study that we have demonstrated various different intelligent compaction system around the country. And that's when we recognize a different type of intelligent compaction measurement values that have named differently. So we create a term called intelligent compaction measurement value to as an umbrella term for the metrics such as compaction meter value, CMV, CCV, HMV, Eval, and KB value. And Cesar are going to take kind of touch on those shortly. And for this research project, it started in 2019, but with a slight delay due to COVID, we finally have conducted a few studies last year during the mnroad reconstruction. And the report has been wrapped up, and as I mentioned, in March, and will be published pretty soon. And people always ask for what did level 1 or 2 or 3 and 4 is for. Since I'm going to touch on the summary of what the different levels are, once our report is published, we have an appendix that show a very detailed technical background about different levels from level 1 all the way to level 5, and in technical detail, the theory and application and implementation. Without much ado, I'll pass on to Cesar to talk about what we have done for this research. It's all yours, Cesar.
Thank you for the introduction, George. So my name is Cesar Tirado. I'm working at the University of Texas at El Paso at the Center for Transportation Infrastructure Systems. So I'll be presenting the results of this study that we conducted last year towards evaluating levels 3 and 4 of the intelligent compaction measurement values in some cells that we tested at mnroad. And first, I want to thank, obviously, George for making this happen, and
Cesar.
Dr. Rahel Nazarian.
I'm sorry to interrupt. We aren't seeing your presentation yet.
Oh, you're not seeing the presentation. Okay. I thought I was sharing it. Okay, there it is.
Great, thank you.
Thanks. So, as I was saying, I want to thank George, Dr. Rahel Nazarian, and our team, Sergio Rocha, who is our instrumentation guy, who without him we wouldn't be able to collect the data, I guess. Also Isaac Zuniga and Abbas Tagabi, who all work together to make this happen. Okay, so what is the intelligent compaction? As you know, this technology allows you to see or measure how well compacted or the level of compaction of pavement structure in, continuously, as opposed to spot tests that you go with like with a flectometer or following with a flectometer that you test on a single spot. Here, you're continuously measuring as the roller is moving along the section. You're taking measurements continuously. And these measures are coming due to the vibrations of the drum. So these pulses or impulses that you're passing to the ground, and also as well the reaction of the soil or the geomaterials they're going to have. They're going to have an impact on a certain measurements that we're gonna measure along the extent of the site. So the advantage is that it can provide you a complete coverage of the compacted section. So there are different levels, as George already mentioned. So under level 1 to 2, with these methods are using empirical solutions based on the frequency ratios. So for instance, you have an accelerometer that is attached to the drum. So this accelerometer is the one that is capturing the vibrations, the frequency, the amplitude of the measurements as the roller is vibrating and moving. So if you conduct a Fourier transformation, you can obtain obviously the amplitudes and make a ratio of the amplitudes and get a value. And these are the basic levels of ICMVs. You have the IC and the CMV, the HMV, and other parameters that are commonly used by different manufacturers. You also have other means, such as the empirical solution based on energy methods and the rolling resistance. So that is the machine drive power. That's another measurement that is there as well, available. Obviously, these are not really going to tell you. They can tell you the level of the stiffness, but it's not really telling you the stiffness. So there are other more advanced ICMVs, or intelligent compaction measurement values, that are based on mechanistic solutions, based on the static or the dynamic method expressed in stiffness or the reactional force or modulus. So you have others such as the EV, which, if I recall well, I think it's provided by Bomback rollers, and you also have the KS stiffness, which is provided by Amman case rollers. So these are using certain set of equations, again, also using the information captured by the accelerometers, and these are passed to these equations. This information is passed to these equations, and a value, an equivalent modulus value or an equivalent stiffness value is provided to you. And we have been exploring more advanced methods, so mechanistic solutions based on static methods to impact the model, with impact model expressing the reactional force or modulus, or even pursuing artificial intelligence using mechanistic solutions based on dynamic methods and artificial intelligence. So that can give you the modulus as well, or density. So on the NCHRP project 2445 that Dr. Nazarin and his team conducted, the goal was to develop a procedure to measure the mechanical properties of earth materials to facilitate adoption of IC technologies for field acceptance. This falls somewhere in between level 4 and 5, more or less, and those are the methods that we use in this study. If you want more information, there is this report from Federal Highway that talks a roadmap about ICMVs, where you can go and see into more detail and that all the different categories and levels of the ICMV measurements. The components of the IC technology is the following. You do need a data collection kit, a positioning system. You need the coordinates of the latitude and longitude. Obviously, the compaction roller, the IC roller, which, I mean, there are manufacturers that come with the kit already. But for example, here at UTEP, what we did is we developed our own kit that we can go and put on I'm not going to say all the rollers, but most of the rollers that are out there. So this kit consists obviously of these accelerometers that I'm telling you about. And this will produce a compaction map. So you're going to see a map like the one that you see here in this picture, where you can have a different set of colors with different ICMV values. And that map is going to tell you like the relative stiffness of the side. So you can see the uniformity or which side seems to be softer than others. As I mentioned, we have some accelerometers. These accelerometers are mounted on the drum, on the axle of the drum. So as it's moving forward and also vibrating, and we use low settings for low amplitude, low frequency, at least for our study, that's what we use. And there is a reason, because we're no longer actually compacting, we're just doing the process during the proof mapping. So once the section is completed, after compaction, we just proof map the site just to see how well compacted, or what is the stiffness or the relative stiffness of the site after the completion of the construction. So these accelerometers are going to be continuously measuring, as you can see in this figure, the vibrations of the drum. And what we do is we take these vibrations, they are associated to a latitude and longitude coordinate, and we do the calculations of the intelligent compaction measurement value. In this case, we use the CMV, the compaction mean fair value, that we associate to a particular coordinate. So we take a record of 600 measurements and we put it in a single point that you see in this map, which is associated to a coordinate. And we do several line passes. I mean, the width of the line pass is the width of the drum. So it can be around 6, 7, 8 feet, well, 8 feet in width. So that'll be more or less the width of the drum and the extent of the measurement of the extent of the area that you're measuring, okay? The width of the area. So you can see here what the mounted accelerometers are providing back to you. So obviously you have these frequencies, and the main frequency that you're going to see is the fundamental frequency, the one that you decided to operate the roller. So if you set it to operate at, let's say, 25 Hertz, well, that'll be the main frequency that you're going to see. If you do a Fourier transformation of it, you're going to see other frequencies as well. And, you know, the impact of the soil, how stiff it is or how soft it is, it's going to have an impact on the additional harmonics that you're going to see later on at other frequencies. So for instance, here you can see the fundamental frequency as the roller is moving along the site. And you're going to see other frequencies, other harmonics here with obviously lower magnitudes. And for instance, the CMV, the compaction mean value, is going to have, is defined with an equation that says that you're going to have a constant of a value of 300 multiplied times the first harmonic, or sometimes they call it second harmonic, divided by the fundamental frequency, which is the operating frequency. So if you do this calculation, you're going to get a CMV value. Obviously, depending on this on the site, the peak that you're going to get for the other for the first harmonic, it's going to be can be higher or smaller. So when you make the ratio, you're going to see an impact on the, the stiffness of the soil will have an impact on this in this parameter. Other measurement values like the CCV makes use of other more complex equation. It's going to use other harmonics like the triple harmonic or a half harmonic to develop a new equation, and it provides you another value. And they are not necessarily equal as the CMV, but it's another value that is reported and it's used by other companies like Sakai. And there are certain advantages of one method or the other. One of the things that we have seen is that as it gets stiffer, for example, the CMV can go up and then suddenly can change trends. And so instead of going up, like if it's really stiff, the material, it can go down. So we need to be aware of those issues with this type of ICMV values. So as the roller is moving, you're going to be getting all this information. Notice those points that I was telling you. And normally what the rollers do is that, the ones that come already with the technology, they're going to grid the data. So if they have a single accelerometer, well, they're going to extrapolate the data, the measurement, along the width of the drum. If they have two accelerometers, let's say at the edges, well, it's going to interpolate between the points and interpolate along the width of the drum. So instead of having a single point, you're going to have a width of several points. I mean, you're going to have a length of several points along the width or along the length of the drum, and you're going to be collecting more data as it moves forward along the extent of the section. So once you do that, and this is done, you can see that almost in real time, or actually in real time, you have the screen in the compactor, you're going to be able to see that a map is going to start to develop as you move forward. So you're collecting the data as you're compacting, and you're also recording the number of passes as you move forward when compacting. This information is useful, especially if you want to compact the section, but in our case, in this study, we just use it as, remember, during the proof mapping process. So our intention was to proof map the site after compaction to see what was the uniformity, what were the locations where you have weak areas or less stiff areas, let's call it less stiff areas. And obviously, we want to use this information to be able to calculate modules. So here are two maps of the sites for the subgrade and the base. Notice the colors. I know it's a little bit blurry, but you know, like for example, the subgrades, you can see two colors which are ranging between 0 and 10. While you put a stiffer layer, then you'll start seeing other higher values for the CMVs. Now, as part of the NCHRP study, we identified that one of the things that is important is the variability of the measurements, because that one is going to tell you how uniform it is, how well compacted, well, how uniform the site is compacted. In order to simplify the visualization of the maps, rather than using several colors, we just decided to reduce the colors to 3, to a green, yellow, and red. Now, for example, here is an example on the side. So we have the roller moving forward and compacting. And then afterwards, we generate a map where we decided to create, to kind of like discretize the map so that we can have some sublots, which are defined by the width of the drum, so like about 6.5 feet, 7 feet, and a length that the engineer can specify. So that can be 25 feet in length or 50, depending on the extent of the site. So in this case, we want to have a grade of, let's say, around 4 by 10 or 4 by 11 cells or sublots, as you can see in the figure on the right. So this is a map of the CMVs. So, and we decided to assign the following colors. For the CMVs, we decided to have, okay, if it's green, well, everything that is in green is whatever is above the average of the whole site. So, for instance, what we're doing is that you can see all these lines. Well, if you were to zoom in, you're going to see those dots. Those are the coordinates where the ICMV value is associated. So whatever you see in the rectangle, okay, let's say it's going to have around 37, 40 something coordinates. GPS coordinates associated to CMV value. You get an average, and that's the value that you're going to see on the right. Like one of those values that you see here, like the 58.2 or the 56.5, like right here in the bottom left corner. Well, so now you get a map with those average values. So to assign the colors, you need to get the average of all these cells. And not only that, we assign the colors based on whatever is above the average, we're going to assign a green color. Whatever is less than 75% and the average ICMV value, we're going to assign it in yellow, and whatever is below 75% of the average is going to be assigned a red color. So that's telling you that those cells were less stiff than the average. Do they meet the criteria for compaction like a design module? Well, that's a different story. Here it's just telling you which areas are relatively less stiff than others. And we do the same thing for the variability. We have another map where we do the same thing for the variability, and it's common to see variabilities of 25% within a site. Okay, so we decided to assign values of 25% or less, and we assign, in terms of variability, we're calculating the coefficient of variation. Whatever is the coefficient of variation less than 25%, we assign a green color. Whatever is between 25 and 35, we assign a yellow color, and whatever is higher than that, we assign a red color. Obviously, we want to have it in green. It's not possible in yellow. And whatever is above 35%, well, it tells you that there is a lot of variability in the measurements in that specific cell or a specific sublet.
Cesar, can you advance to the next slide? Oh, okay, never mind.
Oh, no, tell me. Do you want to mention something?
Yeah, there's one slide probably missing for the variance of the map.
Oh, okay. Maybe I have it afterwards.
All right.
All right. So let me explain the testing that we conducted there. These are photographs of the accelerometers that we're mounting. We're measuring two components, obviously the vertical components, and we measure the longitudinal component. We didn't use that one. It's for research purposes, but it's there just in case we want to explore more to see the impact on the longitudinal component. So this is how we instrument the roller. So here, the roller that was used at mnroad, it's a Caterpillar roller that comes with its own, well, it's already an IC roller, comes with the technology, but we also took our kit to capture the measurements. And we do that because sometimes we have gone to sites that we have used rollers that they don't have this system, even old rollers. And obviously, we always do the comparison to see if there is a difference between the measurements captured by the IC roller and our kit, and we have found that we get fairly similar measurements. Anyways, so in addition to that, one of the things that we did is we instrumented the site. We embedded some geophones at certain depths. Let's say for the subgrade, we went, it was 6 inches below the surface of the subgrade, and then we went 24 inches below into the subgrade. And then when they laid on top, in this case, they laid 3 layers, a subbase and then a base. We're always placing the sensor 6 inches below the surface. So why do we do that? Because as part of the process, or as part of the calibration process of the models, we use that information to compare the model that we developed. It's a finite element model, and we compare the measurements to make a calibration. So we instrument one line and close to the edge, and this is where the roller passes, and that's the one that we use to calibrate the model. So the model that we develop is a finite element model, and we simulated the finite element model using the MEPDG equations. With the MEPDG, the MEPDG constitutive model for base and the subgrade. And let me go back to this. And we obtain what will be the responses under the drum. We know what load that the drum is passing, and we know the material properties because we conducted also resilient modulus testing, and we know the profile of the pavement. We know the layer thicknesses. So we compare what will the model give us with those conditions, or what will be the deflections at those particular depths, and we have a comparison with what we're getting from the field. So we found that okay, there is there is no one-to-one relationship. There is always a discrepancy. So we use that to adjust the parameter. I mean, to adjust the responses of the finite element model. And what we do with the finite element model is that we assembled, and we did this as part of the NCHRP 2445 study, a very large database of different combinations of base and subgrade properties, different types, ranging different values. And we use the constitutive models of the MEPDG. So we're varying the K1, K2, K3 within the allowable values, or the ones that has been reported in different studies, and so that we can account for different types of pavement materials. So we assemble this constitutive this comprehensive matrix of different cases. I mean, we simulated thousands of scenarios, as well as with different roller loads. And in order to prepare a neural network so that we can later use to back calculate the modules. Okay, let me go back to the site. So this is the test layout that we prepared. Notice that you can see a grid there. That grid are the sublots. So we did spot testing every 25 feet along the extent of the cell. And we conducted light water reflectometer testing there on top of after the completion of the layers. So we assembled another matrix of different georeference back calculated LWD modules. Okay, so we use that because we're going to compare how well is our model able to predict those moduli later when we pass the roller measurements. So we did, as I mentioned, we did some testing with the light water reflectometer, as well as we retrieved the moisture content because we know that that has an impact on the response of the soil. We retrieved the moisture content as well. We retrieved samples of every single sublot that you see within the cell. And we also, with the help of mndot, we also obtain what will be the density of those cells, at least probably not for all the 44, but we have probably more than half of the cells with measurements obtained with the NDG. We obtain the density as well as the moisture content using the NDG. The other ones, the one that we used, we retrieved with we also retrieved some samples and we put it on the oven to get the moisture of the material. And that was done right away after compaction. Okay, so everything was done almost concurrently. While they were proof mapping the site, we were also retrieving samples and doing the LWD testing. Okay, so this, as you can see here in this map, you can see that you have a grid with different line passes. We have 4 line passes and we label them as A, B, C, D, and we have them with some values that tells you that, okay, we're starting at station 0 and then we're moving to 25, 50, and so on, until we go to the end of the site. So we're doing this every 25 feet. And here you can see the line passes of the roller. And here it's clear that you can see there are some dots there that tell you the georeference locations where we have a CMV measurement. And here there is another one that tells you, okay, we did some spot testing. We went to the middle of the sublot, and we obtained some spot test measurements using the LWD. Not only specific point, we also moved around to capture 3 additional points nearby to obtain kind of like average values for the whole subplot. So once again, this is how the map looks like, and this is for cell 2228. Here you have the data collected by the roller, okay, with the instrumented roller, and this is the map that you'll be able to see in beta. So you're gonna see that you have, like, for example, different sets of colors. Okay, mostly the color that you see towards the left, those are the lower values. With our kit, if you pass our information to beta as well, this is what you're gonna see in beta. So the maps are similar. You're gonna say, well, there are some difference, slightly difference. I mean, the area of the red is probably a little smaller. Well, have in mind that the other one is grading the data. It's this extrapolation or interpolation that the kit with the Caterpillar roller is doing by as it moves forward. So it's using the value along the extent, the same value that the accelerometer is measuring along the extent of the drum, while ours is using just, well, we're not integrating, we're just using the points as it moves along the section. So what if we transfer this to this method that we have of using subplots? So this is how they will look like. Okay, here are the CMV values for the cell 2228 and cell 2229. Do the colors match with the ones on beta? No, because the ones that you see in beta are based on a range of values. So you're going from 0 to 10, 10 to 20, and so on. Well, in this one, remember, we're assigning the colors based on the average. So, but one of the things that we can identify is that the left side of this section seems to be softer, and that is something that you can see in the other map as well as in this one. And that is something that we were able to identify, and we even were there testing with the algorithm, and we could clearly see that, okay, we felt that the side that was closer to the left in the map seems to be softer than the rest of the section. So these are the maps with the color-coded system. And this is the coefficient of variation. Same thing, but now we're calculating the coefficient of variation of the measurements within the cell. And whatever we obtain, and notice that the values are around 22, 25, 29%. Well, these ones are the ones that tells us how uniform is the site. So, well, you can see that at least in 2228, cell 2228, you don't see red colors. You do see some in 2229. And there is a reason for that. Those cells that you see at the bottom, that's where the roller, where we turn on the roller and we started compacting. We started measuring, proof mapping. So that was the limit of that cell. We were very constrained with some construction that was happening on the adjacent area, the adjacent cells. So that is reflected on the measurements. In addition to that, in order to do some quality control of our data collection, we do, since we're calculating the CMV values, we do check what are the frequencies, you know, the operating frequency using this Fourier transformation. You can do that with all the measurements. When you pass all the measurements, you can do the Fourier transformation and obtain the operating frequency, or the fundamental frequency, which should be the same as the operating frequency of the roller. So notice that here you see the value of 23.3 consistently. Notice that the speed, we also check the speed, and one of the recommendations is to keep a constant speed. In this case, we're using a speed of 2.3 miles per hour. So we want to keep it like around that number, close to that 2 to 3 miles per hour. You don't want to have a change in the speed, because that's going to have an impact on the measurements and the quality of the measurements. So, for example, recall that in the bottom corner of cell 2229 was showing some red colors for the variability. So that's where we were gaining speed. And remember that I mentioned that we had this constraint of there was some construction on this adjacent to that site, okay? So that is reflected. So what we can do is, well, we can remove those cells or we have to do something, okay? That is a decision the engineer should make. So notice that here the color-coded system, we're applying the same color-coded system. It's a little bit different because we want to see, okay, you can, for example, the frequency, you can vary it plus minus 10%. So whatever is plus minus 10% is green, then more than that is yellow, and beyond 20% we have it red. And we do the same thing with the speed. And this is something that an agency can change based on how uniform you want the level of compaction. We do the same thing with the LWD modulus. The LWD modulus, we scanned the section, we do some spot testing. Remember that, like, for example, there is the mark there in that picture showing, indicating where we have to do the spot testing. And we also test on the sides, like 2-3 feet around that area to obtain to see how uniform it is as well, and obtain a single representative value for the cell, for the sublet. So here you can see the results for both cells. Notice again that the results here seem to indicate that the left side is less stiff than the rest of the lines. And as I mentioned, we did some resilient modulus lab testing in order to obtain parameters of K1, K2, K3 for using that we're going to use and pass to our neural network that we developed. So this is the MEPDG model. Actually, we're using a modified version, the one the equation provided by OI. It's a little bit different. We identified, well, in another study in CHRP 10-85. No, yeah, I think so. We identified that this model seems to work a little bit better for predicting the behavior of the materials. But you know, in that report and also in all the other reports like in CHRP 2445 and in this one as well, the one that is coming from this study, we do have the means to go from one constitutive model to another. So to convert from the K1s of the OIS model to the MEPDG models. So here we want to obtain that information because the behavior or the modulus that we're going to get will be affected by the moisture content of the site. So we did some laboratory testing to evaluate what were the values of K1, K2, K3, and these are the ones that we need for the model. Okay, so we did some comparison. We compared the displacement that we obtained with the finite element model and also the geophones measurements. So here we have the testing that we conducted this last year in these two cells, and also we're comparing with what we obtained in a previous test that was conducted in 2017. And same thing, we're getting the same calibration or adjustment factor that we obtained before, which is a value of around 3. Okay, so what we're doing in the mapping process, we're obtaining a map of the CMBs, we're obtaining the map of the variability, and we're obtaining other maps such as like the dynamic drum force, which is also calculated using the accelerometers, using the equation, one of the parts of the equation that exists there for relating the stiffness and the force, or for calculating the contact force that you're passing from the drum and the roller to the soil. So how to implement this method in order to back calculate the modulus? Well, first of all, you have a lot of areas, and obviously no one wants to go and test with the algorithm all these sublots. There are just too many, and it'll take too long. You want the results quick. So the idea is that you go and identify 5 sublots and do testing there with the LWD. We're going to use the LWD to kind of like back calculate the modulus or estimate the modulus of the whole section, but using the intelligent compaction measurement values. So with the LWD, you select some sublots, and these sublots, they must have, they need to be as uniform as possible. So you need to have cells that have low variability. Okay, that's the one condition. It's not reasonable to go and select a sublot where the variability is high because you don't really have confidence on the uniformity of that sublot. So we select the ones that are green, and those are the ones that we use to develop another relationship. So, and this is where we came up with two different methods. One using a neural network using the finite element model, and another one because for the finite element model, you need this resilient modulus testing K1, K2, K3. Not all UTs would like to pursue that approach. The other method is, okay, well, let's say you don't have this option available. You can also do it with using the LWD data and also use or do local calibration there by using the LWD modules. And we found that if we can do it with the drum force, and we're actually exploring the means to do it with the CMV as well. So we develop another calibration factor. So we have these two parallel methods, two different parallel approaches. Okay, so as I mentioned, we select the cells with the lowest or with low coefficient of variation. And then we move to the other map, like the CMV or the drum force map. And we also get the LWD modulus from the map from the LWD modulus. And from there, we're going to get these relationships. Okay, and this is the method with the drum force. You'll get another map with the drum force, which can be calculated. This is not very complicated because it's coming from known information from the drum, from the roller, and the accelerometers, the acceleration measurements that you get from the accelerometers. So this was the local calibration for the specific cell of 2228. So once you do that, you pass it to this neural network, and that we assembled with the finite element model, supplying input parameters such as the K1, K2, K3 parameters, well, actually K2 and K3, the LWD modulus, in order, and then obviously you're passing what was the other parameter? I think it's a CMV that you pass to the neural network, and then you're gonna back calculate, that neural network will back calculate the modulus with the information that you supplied along the length of the site. So this is how the result will look like. You're going to have the chain edge and also the modulus on the y-axis. So as you move forward, this is what you're getting with the LWD modulus. Notice that what we're doing is that with the chain edge, we're getting an average of the 4 rows A, B, C, D for every single location of the chain edge of 0, 25 to 50 feet. And we show there also the standard deviation along that row, and we're moving along the row. So maybe I can indicate here. I don't know if you can see my mouse right there. We're getting an average of every single row of sublots. So we notice that this method seems to predict the modulus, the extracted modulus, and seems to relate well with the LWD modulus. If you were to do a one-to-one correlation, it's not going to look as well. But if you look at it from the side, like, okay, now let's take into account that, okay, we have knowledge that there's going to be variability. But if we take into account and also represent the average values and show the variability with the standard deviation, that it seems to be able to predict the behavior well. Have in mind that here, even though I'm showing the LWD modulus along the whole length of the section, this is not something that we're going to have in the field because we only have the LWD modulus of only 5 sublots. So we're actually extrapolating using that information in order to get the modulus of the site. So here we have the data for the subgrade of 2228 and the subgrade of 2229. So it seems to behave rather well. Same thing for the subbase. And same thing for the base. So now what if you see the whole section? What about all the measurements? Obviously, there is going to be variability. So this is the data for both 2229 and 2228, the LW modulus versus the extracted modulus. So here we're getting an average value, and the error bars are telling you what is the standard deviation that you see of the whole site. And we have some bounds here of 25%, just to indicate that this is the level of variability that you'll be expecting to see. We did a comparison to what we did previously in 2017 at mnroad as well, and notice the ones that are in black are shown here. Those sites were more variable than the ones that we evaluated this time. And we have learned also. We have been cleaning the algorithms to remove other frequencies. So there has been some changes between what we did back in 2017 and last year. What if you want to do it now and you want to back calculate the modulus of the layer? Rather than, the ones that I was showing you were composite. What if you want to go and do it for the layer? Well, now obviously you're going to deviate a little bit more from the line of equality, but still there's going to be some reasonable level of acceptance that we're able to predict the modulus more or less properly. So have in mind that here we're back calculating the layer modulus. Let's say the subbase modulus separated from the subgrade, or the base modulus separated from the underlying layers. And we're doing both for the LWD and for the equivalent modulus obtained with the model using the IC data. Okay, so just to conclude this, I think I went too long with this. So you can see that these methods that we are proposing, and you can find out more in the reports, are able to extract the mechanical properties of these geomaterials. Obviously, we need to do some, or at least we did some calibration on on our models. We ended up having the same calibration factor, so it seems that it can work with different material properties. So the measurements between the numerical results and the field measurements show similar trends, but also there are some systematic differences. All right, so just to conclude, just to mention that the final report is about to be published by NRRA, and now the next phase that will continue this study will be to test the IC certification specification framework. So that concludes the discussion that I have here. So I don't know if you have any questions. I'm going back to you, Lauren.
That's great, Cesar, to share the latest and greatest from our study. And really, this is laid the foundation for future IC certifications that Cesar mentioned about. In the report, at the end of the report, what is one chapter that will focus on the framework for the IC certification? Why we do that? I think the goal is not just to use intelligent compaction for quality control, but eventually for acceptance. And as Cesar just mentioned about IC can have a 100% coverage of the compacted area. It can only, the 100% of coverage area can provide you the uniformity information versus a spot test. So that's the goal for us from our research project to promote the higher level 3 and 4 and above ICMV that provide the stiffness value and modulus value from level 3, and level 4 and above can give you layer specific modulus. So that's really the goal for this research. And this is only the first step. and the next step is to implement it in the certification program. Any questions for Cesar or me? And I mentioned that there's a very detailed technical information about how the level 1 to level 5 ICMV being classified based on 4 different criteria. First one is to correlate to spot test, as Cesar just demonstrated with against, say, LWD test. And then the second is to provide measurement value when the drum is in the double is bouncing or double jumps. So that's very critical toward the end of the compaction that we still need to get that information, and that's Cesar had mentioned about. And the third criteria is to provide a layer-specific modulus. And only using modulus, you can do a layer-specific, not stiffness. Then you will not be restricted by the loading footprint. And finally, the fourth criteria is once all these first 3 criteria have been met, we can enhance the model using the AI or machine learning, as Cesar had demonstrated from the 2445 NCHRP study. So we're still evolving in this area of intelligent compaction. We hope the level 5 ICMV will be implemented, will realize in the real world, and that will provide you a very reliable layer-specific modulus and also density. Any questions? As I mentioned, you need to find more information about this project. You can go to the link on the mndot project website, and we'll post the final report as soon as we heard from the mndot publication department. And we also have a website called intelligentconstruction.com that provide a lot of our further studies that related to the IC. And with the current study by Professor Sohail Nazarian at Turner Field Bank, and also our study with Federal Highway for IC from Foundation. And all these efforts are taking the focus of IC back to the foundation and geomaterial again, after many years been focusing on the asphalt material. Cesar, any final comments?
Well, just any questions that you have, please feel free to contact us. We're here to discuss this, and if you have any ideas, any recommendations, any concerns, please share those with us as well, because I mean we need to refine and improve this process. So any comments are welcome.
And as the last slide that Cesar showing here, happy ICing. I see. All right, Lauren, that's all we have today.
Wonderful, thank you. I'm not seeing any questions or comments in the chat, so we do have a couple minutes yet. If anybody had something, they could unmute and share that. Otherwise, we can log off for the day. I'm not seeing anything, or hearing anything, so we will just adjourn and hope to see everybody in June as well. Thank you so much for your time this morning, and thank you for the presentation. Now I'm seeing some thank yous in the chat, so thanks to everyone who attended, and we'll see you soon.
Thank you all. Thank you for attending.
Thank you.